So in this video, I made you a promise, and that promise was we were going to talk about a different type of example, a different type of hybridization theory. And this hybridization theory is going to concern a triple bond. Now, I don't think that we've done examples of triple bonds, but we can have them. So this is a chance where carbon can actually form a triple bond to another carbon, and each one of those has the fourth bond to a hydrogen. Okay? So in this example, the formal charges of carbons are still zero. They have one electron from each bond, 4 valence from carbon, 4 minus 4 is 0. And the formal charge on the hydrogens are also 0 as well. So this is a stable Lewis dot structure. Everything has no formal charge whatsoever, and everything is good to go. They all add up to 8 that need to add up to 8, and hydrogen has 2 apiece. But the difference here is that this particular carbon and this particular carbon, they are attached to only 2 atoms, okay? We have an atom on the left, which is hydrogen, and we have an atom over here to the right-hand side of the first carbon, which is another carbon. So 2 atoms, that's it. I know that there's 4 bonds in total, but there's only 2 atoms that it's connected to. That's the way that I want you to think about this. So I'll go back to the electron configuration, 1s2, 2s2, 2p2. And in the first block, I have a double, and in the second block, I have a double, and then the p blocks are degenerate, so there's 3 options, and there's one here, and there's one here. So we said, in order for carbon to get 4 bonds, and that's what it has, it does have 4 bonds. In order for it to get 4 bonds, we have to erase an electron and we have to promote it to an empty p orbital. So this sets up the entire narrative of a possible hybridization theory. Is it sp3? Is it sp2? Or is there a different sp hybrid that we can choose from? Well, that's what you're going to figure out here. There is a different option. So look at what I said. 2 atoms that's attached, a hydrogen and a carbon. We're not looking at the number of bonds. We're looking at the different atoms that are attached. There's just 2 of them. That's it. No more, folks. So we only need to utilize 2 of those boxes. And this is an S and it's 1p. So this is called an sp hybrid, and this is sp hybridization theory. So what happens here is that this carbon is attached to another carbon, and this sets up the first bond. Well, we have a empty p orbital that did not get touched, right? So I'm going to draw a figure 8 up and down that has 1 electron in it. And then in the other carbon on the other side, the same story is there. This carbon has an empty p orbital, not an empty, but only one of them there that has 1 electron, and those can be blended and shared just like they did in sp2. So this can overlap, and when this p orbital overlaps, that creates the second bond of the triple bond. Do you see where I'm going with this? So we've already talked about this first one. We've now talked about the creation of the second one. It's the same as what it was in sp2 hybridization. Now, though, we have an extra p orbital that did not get used. And this is also another figure 8 shape. So I'm going to try to draw this one backward. There's the first part of the lobe, and then here is the front part of the lobe. And this one has an electron, this one has an electron, and that shape will blend and it will overlap as well. So think of this as pointing towards you and pointing away from you. This is the orientation of that p subshell. So the first overlap happens to create a second bond, and then a second overlap happens to create that third bond that we call a triple bond at this point. Again, it's extra overlap. This now has a total of 6 electrons. So you talk about negative areas. This is a very strong negative area in molecules whenever they decide to happen. So 6 electrons in total. It's extra electron, it's extra overlap. You can imagine these carbons getting pulled closer and closer together because there's kind of extra glue that holds them together at this point. Now, that doesn't mean that they're not reactive. It doesn't mean that they're stable. It just means that they're closer together. There's more things that are holding them together and preventing them from splitting right away. But this is truly a strong negative area of the organic molecule. All right, so this is the story with triple bonds, and this is how they're made. So it's a sp hybrid, and this frees up 2 orbits. This first orbit overlaps with a neighbor to create a second bond, and then this third orbit overlaps with a neighbor to create the third bond. Here's a representation again of sp that you might see in your textbook, and that's exactly what they're trying to depict. They're showing you that 2 atoms are on this carbon, so therefore you only need 2 of those. Okay, and that frees up 2 p's, and those p's will overlap. So the first overlap happens here, and the second overlap happens here. And that is what creates that third and final bond for you in sp hybridization. Down here at the bottom, you're seeing the typical way that we draw the structures. They're giving you a little bit of geometry here. Again, we'll talk about that all at once in a different video. Here is the ball and stick model. As you can tell, this is a very linear, flat area of the molecule whenever a triple bond happens. There's no kinks or curves in those types of molecules. And then here is the space-filling model that really does away with the sticks because those sticks really are not there. And then finally, here's the electrostatic potential map. And as you can tell, this area is strongly negative. That is why this is red. It's telling you there's a lot of electrons here. On the end caps, those are blue, and those are positive areas. Here's another representation of the sp, and what they're trying to show you here is that the orange-yellow one that's showing up on your screen, this would be like to the hydrogen, and this would be to that carbon. So those are the traditional single bonds that you saw drawn on that sheet of paper. However, the formation of the double bond happens with the overlap of that p orbit, and the formation of the triple bond happens between that one that goes behind you and in front of you. So there is the triple overlap that begins to form. Here's another basically depiction of everything that we've talked about so far. Again, they're calling it sigmas and they're calling it pi's whenever they can find them. So shorthanded representation, that is what it's all about. And then here maybe is a better depiction of a 3-dimensional fashion of what we're talking about. So here's your initial bond between the 2 carbons, and then the blue orbs, you can see them smudged together. There's your second bond, and then the purple orbs, there's your third one. So there's your triple bond. And you put it all together, and you get this nice clean C, triple bond C with a hydrogen and with a hydrogen. So here's hybridization of what we would call a sp bond or sp hybrid. Now, are there other things than carbon? And the answer is yes. There's other things rather than carbon that can also hybridize. A lot of times we see nitrogens, we see oxygens, and those will hybridize in order to make them work as well. So we will talk about those, but I'm not going to talk about those right now. We'll address those at a different time. I just want you to focus on the basic carbon-based sp hybridization in this video. Okay. Another thing that I want to mention is that single, doubles, and triples are very common bonds that you are going to see in organic chemistry. So a single bond we know is a sigma, and a double bond we know represents a pi, and pi stands for p, and that represents 1 p overlap. And a triple bond are actually 2 pi's. It's 1 p overlap and a second p overlap. So there's 2 pi's that are included in that triple bond, as well as a sigma. All right, so this is a build-up process. That's what a lot of people have confusion with. If I have a carbon-to-carbon bond, this is a sigma bond. If I have a carbon double bond carbon, I have a sigma bond, which is that first line, and then I have a pi bond, which is that second line. That's the overlap of the pi, or the p orbits. And then if I have a triple bond, this is a sigma for the first line. It is an overlap of a pi or a p, so that's 1 pi, and then it's another overlap of a p, which is our second pi overlap. So that is how these things are structured. So sp3s are always single bonds, sp2s create the double bond, and the sp creates the triple bond. That is the shortcut that I want you to remember, really. And we'll do a few of these examples so you know what I'm talking about, and that's not just a vague tidbit of information. So we'll go through and we'll talk about this maybe in a little bit more detail. Other stats on orbits. We have sp3 orbits, sp2 orbits, sp orbits. And I told you that we will have a summary of all of the geometry that happens here. So I first want to talk about sp3. sp3 are 4 bonds in total, right? So those 4 bonds are evenly around the carbon. It says 109.5 bond angles. What that means is that a bond angle is the angle that's represented here between one bond to the next. So it looks like it's 90 degrees on the sheet of paper, but it's a little bit larger than 90 degrees because this is the way I represent it on a sheet of paper. But if I really want to get them further apart, it's actually 109.5. It's a little bit bigger. So that's kind of surprising to some people just because we have a tendency to make everything squared off like this when we draw them. Another thing is that the bond length. So the bond length here is going to be 1.54 angstroms. Angstrom is basically a unit that is like meter or millimeter or centimeter or micrometer or picometer. The problem is that an angstrom is a super tiny length, as you can imagine, because we're talking about lengths of bonds, and this is 10 to the negative 10th. I don't think that's anything that you have to memorize. I don't think that that's something that I'm going to make you do any kind of math with, but it gives you an idea of how super tiny this thing is. So imagine writing 9 zeros in front of 1.54. 0.0000000000154. That's how short that this particular bond is. sp2s are a little bit different. sp2s are 3 atoms that get attached, right? And because of that geometry, the angle of those bonds change, and this angle is 120 degrees. That bond is also pulled a little bit shorter because there's a double bond that's involved here. So that double bond is extra glue. It holds the 2 carbons closer together, and you see that in the bond length. That bond length begins to shrink. It goes from 1.54 to 1.33. And then finally, the sp orbits. The sp orbits were basically a carbon that's attached to 2 others. So that means that one of these had to be a triple bond. As you can imagine, this is a pretty much straight line. That's why these bond angles are 180 degrees. The length of this particular triple bond here, that length is even closer because it's pulled closer because there's more electrons and there's more glue that hold them closer together. So this goes from 1.33 down to 1.20, so that bond length gets even shorter. And there's a little bit of information about geometry here. And we kind of mentioned that in our description, right? We said these were tetrahedrals, and these were trigonals, and these were linear. So there is your story of hybridization theory in organic chemistry. Okay, so hybridization theory is basically a way that we can go through and talk about different aspects of an organic molecule on a scientific level. We can start talking about sigma and pi bonds. We can talk about hybridization theory, sp3, sp2, sps. We can talk about bond angles. We can talk about bond lengths. And all of this plays a role because it helps describe why carbon really can form 4 bonds when only 2 electrons initially are available for it to use. This hybridization theory helps explain that whole narrative. All right, so that's all that I'm going to say in this video. We've now kind of summed up the 3 versions of hybridization theory that happens in organic. All of this was probably new information for you. I know that they cram it into what they call remembering general chemistry, and I don't know why they did that, but they did. So, new information that you're taking away. We'll come back, we'll do some examples, what kind of questions that I'm going to see about hybridization theory, and you'll really see at that point how easy that this stuff will be. I promise you, it will be easy. Trust me. All right? Again, I've been doing this for a while. I know when people click, and when this happens, people are so swamped, they think that they're not understanding it at all. They're like, what on earth is going on? What did I get myself into? And then they see the example, and they're like, what? Is that all that it wants? And I'm like, yeah, that's all that it wants. So you'll see that in the next video. I promise.